Okay, this is part 2 of, right, I can never remember, lecture 4. And in this one, we're going to talk about the specific constituents of an atom. Last one was history. Okay, so now we have our modern theory, because it is still a theory. And very likely we're going to make a discovery, or you guys will make a discovery in the future that's going to tweak the model we use a little more. That's okay. It's one of the fun things about science. We're always learning. So we have, whoops, a nucleus where the proton, the positive charge, and the neutrons live. Very, very compact. And then the electrons are around it in specific orbits, and there's lots of space. This is what makes up our world. That's why I said there's really no, matter is not really matter. There's more space than anything, but it's the forces that are involved that keep us from able to just, why you can't just put your hand through the desk, why you can't walk through a wall. It's because of the forces, which is really kind of cool. All right, so the subatomic particles, I'm sorry, I apologize. I was going to look this up specifically and I forgot to, but you can do it because if I remember correctly, the proton, the neutron, and electron all were split from the original source of energy. So they're all pieces of a whole. And I realized in the Big Bang, everything split from nothing. Still figuring that one out. But these 3 parts were all part of a whole. And if you look at it, the charge of the proton is identical to the charge of the neutron. I'm sorry, the electron. So that makes sense because it has to be balanced. So you would need for the proton and electron, positive and negative, to be identical to balance each other out. And the electron's really tiny. So its size is almost insignificant. However, because it does have mass, it's considered a particle. Because an electron behaves both as a wave and a particle at the same time. It's one of the great mysteries of chemistry. And we can call it a particle because it does in fact have mass, even though it's super tiny. But look at this, the neutron and the proton are almost the same mass, almost identical. So that again goes to support that it was part, it's like these are the 2 halves and this is the little bit of third little fly out that, I don't know, that's just kind of as far as my imagination can go, but it's fun to think about. So those are the critical particles that make up an atom. And of course, now we know that it actually is even smaller particles, but this is where we'll stop. That's quantum chemistry. All right, so this is your best friend, the periodic table. It is on every wall. We have it on coffee cups. It's on every surface. You will be able to use it on your exams. And you are going to learn to read it. So first, this is the main one we're going to work with. We're not going to work with the intertransition metals, which is that bar that you usually see below it. So you have 3 different types of elements. You have metal, nonmetal, and metalloids. Nonmetal are over here. And hydrogen behaves as a nonmetal, so it actually would be over here. It's over here because it has 1 electron, and this group has 1 electrons. So sometimes you'll see it in both places. Sometimes you'll see it here as well. So for behavior, know that it behaves as a nonmetal. There's on the right-hand side. You have to know where everything is. Metalloids are in this ladder like in between. A metalloid behaves as both a metal and a nonmetal. Everything else is metal. Going down, we call that a group. A column is called a group. So this is group 1, group 2, group 3, etc. The rows are called periods. So period 1, period 2, period 3, period 4. Each period is a new shell where electrons live. So period 1, and each space is 1 electron, also 1 proton. So hydrogen has 1, helium has 2. Now we're going to move to period 2, so you now have a new shell. It's outside the old one, a new orbit. And we have lithium. Lithium has 3 electrons because 2 are in that inner orbit. And then it has 1 outside, and that's called the valence electron. So we're going to get to that. All right. Know these symbols. If you look at the periodic table, there's a number over each element. The bottom number here is the mass. This is the number of protons. Number of electrons can change and number of neutrons can change, but number of protons never changes, and you do want to know that. So in an element, just as it is on the periodic table, it has this, it's balanced, right? So it has the same number of electrons as protons. So nitrogen has 7 protons, it has 7 electrons. That can change, and when it changes, we call it an ion, but as an element, sitting there, nothing has been done with it, it has the same number of electrons as protons. Okay, that's very useful because we use the symbol, here's an example with carbon, to describe an element. So that you put the element symbol here. So carbon is C. Go back to periodic table, there's C. There's carbon right there. So that's going to be to identify what we're talking about. The bottom number is the number of protons. And that is called the atomic number. That's the number when you look at an atom on a periodic table, that's over it. So that's the number that's associated with the atom, is the atomic number. That's the number of protons. The top number is the mass number. It's the components that are giving the atom mass. So it's what gives it mass? Protons and neutrons. So added together, that goes up in this corner. So this is both of them together, and this is just protons. So we can look at this and know this has 6 neutrons, because 12 minus 6 is 6. Because there's no charge over here, which we'll get to, which would designate an ion, we know that it has the same number of electrons and protons. So this has 6 protons, 6 neutrons, and 6 electrons, and it's carbon. That tells you a tremendous amount of information about this element with this symbol. So know this symbol, know how to decipher each of the components when you're given partial information. That's sufficient. All right. Now, I said you can have different numbers of neutrons and electrons, but you will never have a different number of protons for an element. All hydrogen will have 1 proton. All nitrogen will have 7 protons, no matter what. But you can have different numbers of neutrons. This happens naturally. It can also be made in the lab. We call those isotopes. So this number up in the top corner was the number of protons and neutrons together. So that's what's going to change when you have an isotope, is this upper mass number changes. So hydrogen, the hydrogens commonly in nature, 99.985%, has a mass number of 1. It has 1 proton. If you had the atomic number down here, it would also be a 1. It has 0 neutrons. Deuterium, which occurs naturally, has a mass number of 2, which means it has 1 proton, because hydrogen always has 1 proton. Look at the periodic table, there's your cheat sheet. So it has 1 neutron. And then tritium, which is made in the lab, still has 1 proton, because hydrogen always has 1 proton, so it has 2 neutrons. This makes a difference because this is mass, and when you change the mass, you change the chemical behavior of an element. So that is an isotope. So make sure you can identify what an isotope is and how we identify it when we're given the symbols. The other situation is an ion. This is when you gain or lose electrons. And this happens, whereas isotopes exist as a stable percentage of the element in nature. You just have a specific percentage of each isotope in nature. So often elements exist as a combination of isotopes. That's just how it is, how they exist naturally. Ions are made, and it has to do with the reactivity of the element. And the reactivity has to do with the valence electrons and the fact that every atom wants a filled shell. It wants all of its electrons paired. That's the lowest energy level for any atom. And the lowest energy level is always the driving force for any chemical activity, characteristic, property. It's going for that lowest energy level. Electrons drive everything. Chemistry is all about the electrons, but it's energy drives everything. So the charge has to do with the imbalance. And I went into this in detail in the live lecture. So if you haven't watched that, make sure you watch that, because since I have that on the whiteboard there. I'm not going to repeat that. But go to the live lecture if this is confusing and see how I've worked that out on where this charge comes from. But it's the imbalance of protons to neutrons. Magnesium loses 2 electrons. So where originally it had, let's go to the periodic table, magnesium normally has 12 protons and 12 electrons. If it loses 2, it now has 10 electrons, but still has 12 protons. So it has an imbalance charge, and it actually has more 2+ charge than, so it's 2+ more positive charge. So we put that charge up here. That's how we know something is an ion. We write it like this. And the plus goes after it. It doesn't go ahead of it. So if you lose 1 electron, you now have 1 more protons than electron. And so your charge would be 1+, because that's your imbalance. So it would be B. So let's look at these. If you're given this symbol, you can figure out how many of each of the components are in that atom or that element. So boron, this particular boron has 5 protons, position atomic number 5, 11 total protons, neutrons, because the mass number is 11, the things which are giving it mass. Well, we know it has 5 protons because it tells us. 11 minus 5 is 6, so there are 6 neutrons. There's no charge on it. Therefore, it's not an ion, it's an element, and has the same number of electrons as protons. So it has 5 electrons. Because it's balanced, there's a net charge of 0. Okay, let's look at this one. How many protons does this have? Well, that's that bottom number, so that one's easy. 26. How many neutrons? You want to subtract 26 from 54. So 54 minus 26. Right. If I try to do it in my head, I'll probably make a mistake, but do it on your calculator. Oh, you would have gotten it right. It's 28. Now, electrons. This has a charge. So if we look at net charge, it's +2, right? That means it has 2 more protons than electrons. So if it has 26 protons, how many electrons will it have? Right? It's going to have 2 fewer, it's going to have 24. So with the symbology, you can figure out each of the constituents. Okay, let's look at sulfur. This is a sulfur ion. This is an anion. We call it the sulfide anion. So the net charge is -2. So notice we write it on the ion with the number and then the charge, but when we talk about the net charge, we say it in reverse. Oh, and that's an error. That should be 2, not 3. Well, I can't fix it here, but never noticed that before. So make sure you notice that that's an error. It should be a -2. It had 16 protons, right? All right, there's our error. All right, you know what? Skip that one. Let's just see so I can go back and fix it. Or you can fix it and see if you can come up with it right. If we go to sulfur, sulfur's over here. Sulfur has 16. So fix that. So this should be 16, and this should be 2 minus. So 33 minus 16. All right, so skip this one, but you can go back and actually fix it. This is correct. Once you go back in and finish and fill these in correctly. My apologies. I'll have to go back and fix that. So this is gold. Au is gold. It's not an ion, therefore the net charge will be 0. How many protons does it have? It has 79, because it tells you right there. How many neutrons? No, actually, how many electrons? It does not have a charge, therefore it must have the same number of electrons as protons, which is 79, right? How many neutrons? It's the mass number minus the protons. It's all the items which give it mass, which are protons and neutrons, minus the number of neutrons, which you know. And when you do the math, you get 117. So this last one, you're supposed to find out what this is. So we know it's not an ion because it has the same number of electrons as protons. So I'm going to go, it has 86 protons. So let's go to the periodic table and see what has 86 protons. And it's actually down in the inner transition, which is a different periodic table. But when you find that in the expanded periodic table, you'll be able to give the element symbol, and then the mass number will be 86 plus 136 will go in the upper corner. So make sure you know how to do these, because you will likely get this as a test question. So how many neutrons does this have? We aren't concerned for this question with the electrons because we want the neutrons, which is the mass. So we have 15 protons and 31 total protons and neutrons. So it's 31 minus 15, which, unless I've done the math wrong in my head, is 16, which it is. But how many electrons does it have? Now we have to look at the charge. It has a 3 negative charge. This is an ion. This is phosphide ion. So if you have 15 protons, you have an excess of 3 electrons, which means you have 18 electrons. That's why it has a 3 negative charge, or negative 3. So this has 18 electrons. This is D. As I said, when you look at the periodic table, get back down here. I said the top number is the atomic number, number of protons. The bottom number is your mass, all right? And that's where we get mass from, which you will use a lot. So the mass for an individual element or molecule is defined by an atomic mass unit. And that is based on the carbon-12 atom. The carbon-12 is your standard carbon atom with 12 protons. I'm sorry, 6 protons, 6 neutrons. So it's defined as 1/12 the mass of one of those atoms. Because when you have a unit, you have to define it somehow. So this is how it's defined. And since they knew what one carbon-12 atom weighed, what the mass was, they were able to come up with an AMU. So this is an AMU, and it's used for individual molecules, elements, individuals of anything. We now call an AMU Dalton. You often will see this when you're talking about proteins or DNA, RNA. We use the term Dalton. So you often will see AMU still for elements, But when you get into biochemistry, you're going to use Daltons. And the other thing is that isotopes, like I said, occur naturally. Some of them actually occur in specific significant enough percentages that it affects what the total mass is. So in those, the mass that you see on the periodic table is actually a weighted average. So if this isotope is 75% of it occurs naturally and it has this mass, but 25% of this element occurs as this isotope, that's significant enough. And because the neutron has mass, it actually can change the mass significantly. So what you do is you do a weighted average. You simply say, okay, 75% of the total mass is this. 25% of the total mass in nature is this. So you multiply this mass times 0.75, you get this. You multiply this mass times 0.25, the fraction, and you get this, you add it together. So this is the weighted average of this element in nature, if you consider all of the isotopes. So most of the isotopes are insignificant percentages, so we don't do this, but when it is significant, it exists in a significant enough percentage to make a difference, we do a weighted average. So make sure you understand how to do a weighted average. So if you're given a question like this, which you probably will, you have 3 isotopes. There are 3 different percentages of how they exist in nature. You simply multiply the individual mass times the 0.7955, make it into a decimal. Same with this one, same with this one. Add those together. And I don't have my calculator in front of me to do it, but add those together and to get the answer. Okay, I am actually going to stop here for the parts and pieces of atoms that make them up. So this is the end of part 2. Part 3 will be reactivity.